Alaikum and hello to everyone. This is a second example for turbines. But this time the substance will be a gas. Specifically air. All right, so let's see how to solve this question. So we have an adiabatic turbine receiving air steadily at 1.5 megapascal, 400 degrees Celsius, 90 meter per second. Leaves the turbine at 150 kilopascal, 200 degrees Celsius, and 200 meter per second. The mass flow rate of the air is 0.25 kilograms per second. Given in the question, the specific heat at constant pressure, Cp, 1.005 kilojoules per kg Kelvin, and also the gas constant for air, 0.287 kilojoules per kg Kelvin. Alright, now, so the question asks us to determine the inlet area of the turbine, A1, and then the power output of the turbine in units kilowatt, so work out, So, before we start with the first step, try to write the conditions, so condition, so we know the first condition is based on the work interaction. So it's a turbine, so work in is 0. And then adiabatic, so Q in equals to Q out equals to 0. Okay, and now the third one, since the question does not mention we can neglect potential and energy, but when we read the question there is no values which resembles or which is for the potential energy. So we can make an assumption that the potential energy can also be neglected, because there are no values given, for potential energy. So we can assume that the question asks us to neglect potential energy. Alright, so the conditions we have written. Now for step 1, we try to draw the schematic diagram. So for a turbine, the turbine inlet is on the top, state 1. Exit is at the bottom, state 2. There's a shaft. Shaft will rotate, producing a workout. If you want to write the conditions, we can write the conditions. So P1 is 1.5 megapascal. T1 is 400 Celsius. So we can convert it into Kelvin straight away. Since it's a gas or air, so the temperature must be in units Kelvin. And then we have the velocity, 90. And also we have the mass flow rate, 0.25. At state 2, pressure at state 2, we know it's 150 kilopascal. Temperature at state 2 is 200 degrees Celsius. We can convert it to Kelvin. Kelvin. And the velocity is 200 meter per second. Alright, so these are the step 1. For step 2, the equations we're going to use. So for area, the first equation we should try to use is the equation for mass flow rate. Because why? Because we have the value for mass flow rate, and inside the equation for mass flow rate there is the term for area. So mass flow rate equals to area multiplied with the velocity divided with the specific volume. So we can do it at state 1. Since we want the area at state 1, all of our properties has to be at state 1. So we can rearrange the equation. So to find area, area 1 is equivalent to mass flow rate at state 1 times with the specific volume at state 1 divided by the velocity at state 1. So mass flow rate we have, velocity we have to find the specific volume at state 1. Okay. And then the power output or the work output is from the SFEE. Okay, so write out the general equation. Okay, so try. Okay, the general equation first. Okay, I try to write it very small so I can fit in one line. Come on. Oh. Nice. Okay, all right. Then we cancel based on the condition. So work in is 0, adiabatic turbine, Q in, Q out is 0, and we have neglected to potential energy. Okay, so on the right hand side, on the left hand side, sorry. On the right hand side, okay, and then we rearrange, okay, to find for work output. Be careful of the brackets. Okay. Okay, so this is the rearranged equation. Okay, now, but before we can proceed, remember the substance is a gas. So for gases, okay, H has to be replaced with its specific heat relationship. So H equals to CPT. Okay, so we have to replace it first. Cp is a constant. We can factorize it. Okay. Okay, so this is the equation. Okay, all right, the equation. All right, so actually we can solve it already because we have the mass flow rate, we have Cp, we have T1, we have T2, and the velocity is given in the question. Okay, but we try to do it step by step. Okay, so for step 3, okay, state 1 first. Okay, so what we know is the pressure 1.5 mega or 1500 kilopascal. The temperature in Kelvin 673 Kelvin. The velocity is 90 meter per second. Okay, what we want to find is the specific volume. So we can use the equation, ideal gas equation. Okay, P specific volume RT. Okay, so rearrange it in it. Okay, substitute the values 0.287, 673, and pressure in unit kilopascal. Okay. Okay, so we will get 0.1288, okay, meter cubes per kg. Okay, so we have solved for specific volume at state 1. For state 2, there are no properties to find at state 2, but we can still write it down. Okay, there's no harm done in writing things down. Okay, 473 Kelvin, V2 is 200 meters per second. Okay, don't have to find anything, so we can just write it down. Okay, so finally we can proceed with step 4, which is to substitute and solve. So to find the area just now is the mass flow rate multiplied with the specific volume divide with the velocity. So 0.25, 0.1288. Okay. Velocity at state 1 was 90 meter per second. So we can get the answer as, okay, in meters, in meters square, 0.00358. Okay, but the question, okay, if I'm not mistaken, it asks us in units, centimeter square. Okay, so we have to convert it. Okay, so make sure you know how to convert. Okay, So basically, we want cm square. Okay, we have meter square. Okay, so we have to times with 100 cm over 1 meter times 100 cm over 1 meter. Okay, so we can cancel this and we can get cm square. Okay, so basically it's times with 100 times 100 is 10,000. Okay, so 4 zeros. Okay, 1, 2, 3, 4. Okay, so it's 3.58. Okay, centimeter square. All right. So this is the answer for the first part. Okay. And then for the work output. Okay, so m dot multiply with Cp T1 minus T2 V1 square minus V2 square over 2000. Okay, we substitute the values. Okay, so 0.25, 1.005, 673, 473, 90 square, 200 square, 2000. Okay, and calculator. Okay, we will get 46.26 kilowatts. Okay, so that is the answer for the second part of the question. So we have completed the example for turbine. So thank you for your attention and have a good day.